I'm Jamie. I was in charge of managing the group during the project. We split the group into several different parts to handle all the different parts that would go into the main robot. We split the robot into the hardware, the software and the electronic components, and got different people to work on each part. During the project we had Dan and John working on the code, myself, Shen and Joe working on the electronic parts, and Ivan was in charge of the chassis.
My main point in designing the chassis was to make it as light as possible, because it's the second heaviest part after the actual motors. In the group we decided to make it modular, so if something breaks on it we can replace it. So this is how it became like a constructed kit. So basically the chassis is made out of small plates which in the end go together with bolts and nuts, not that.
For the motor coding, we had to get it so that it went from a standing start to our top speed, like fairly quickly in a smooth linear fashion. And this we all had to have a debug mode where we would be able to see what was actually going on inside the chip. So we had the 4 different modes. We had the race mode where it didn't have any debugging built into it whatsoever, so we couldn't see what was going on, but it would be fast, efficient, and it would actually be the fastest mode out of all 4. We had the debug mode, which showed us everything that we would ever want to know, and the other 2 modes were somewhere in between. The initial idea was to have a completely linear acceleration, so because of how the chips work, this worked out to be 8,000 different steps. But because in the higher ranges, to get the acceleration to work, we couldn't actually get the motor to turn around the corners properly. Now, we have 32 different steps of acceleration, so we'll upload the first timer into that particular wheel, or the first speed into that particular wheel, and then it will, after a certain amount of time, we'll upload the second speed, and then the third, and then the fourth, until we've reached the top speed we required for that wheel.
My name is John and I was responsible for designing the navigation code. Whilst designing our system, we had one of the other problem as we're using TSL and infrared sensors. But furthermore, we have kind of approximated the function of a dual-core system as we've got 2 processors. The idea behind this concept of having the TSL and infrared sensors was to leave time to decelerate when approaching corners, meaning the TSL sensors ahead of the robot, so when you approach a corner, the trend of the corner is saved and starts to decelerate depending what sort of trend is going to come up. Once the infrared sensors, which are by the wheels, flag up, the robot knows it actually has to execute that trend, maybe sort of 90 degrees or something in that manner. As there are many parts in the system that can go wrong, we have included a few debugging methods. First of all, the RS-232. This supports bidirectional communication, meaning we can send commands from a computer, for instance, move straight ahead or turn 90 degrees, and then we can see how the robot behaves. But furthermore, we've also implemented LEDs, status LEDs, to indicate what the robot is currently doing, if it's even running at all, if communication between the individual components is functional.
I also needed to design the sensors, so I decided on the design that used photo transistors, and I chose infrared transistors so that they wouldn't be interfered with by the lights. And we're using 3 of those in addition to a TEOS that we're using as a look-ahead sensor, and that should help our robot see its way around the track.
Okay, I was responsible for the Variboard designing the robot. Everyone in the team made a contribution with regards to circuit design for the robot, and then it was my job to take all of those designs and then work out how they would fit onto the Variboard. The way we did this was by first creating a rough design. So that was basically me redrawing the circuit on just a blank piece of paper with as few crossed wires as possible. And then from that we were able to translate onto a simulated piece of Veriboard, which was basically a grid with holes that would represent holes present on the Veriboard, and rows representing rows present on the Veriboard. After this was done, I performed a test with all the different components being used on the Veriboard, just to check and see how many holes components would take up, how much space they required around them, and then these measurements were incorporated into our final Veriboard design.
During the project, we followed the V-process model. This means that we continually went through stages of creating a design and then testing it until the design was correct. This may have made our design time very lengthy, but should mean in the end we have a more valid system, and that'll save us time that would have been spent fixing errors at the end of the project.
We had some problems in the group with making sure that people completed their work on time and up to standard, but now it's getting to the end of the project and our work is picking up in standards and is more on time than before.